The Lagrange error bound and Taylor's theorem, as well as the Taylor series in general, are often difficult topics for many students to grasp at first. Both these concepts are about approximation and figuring out how accurate an approximation made using the Taylor series is. Since the Taylor series for any function is infinite, it must be cut off at some value of n in order for it to be used as an approximation. The more terms, the more accurate this approximation is, as can be seen here with the sine function. The more terms you add, the more the curve of the approximation gets closer to the actual sine curve. The error is the absolute value of the difference between the function and its approximation, which here in this picture is represented by the area shaded in red. Now, if you add whatever difference there is between the function and its approximation to that approximation, then you should get the value of the function itself. This is the basis of Taylor's theorem, which states that that the exact value of the function equals the nth degree Taylor approximation at a added to some remainder. If you know the exact value of the remainder, there's no need to approximate because the value will be exact. The remainder itself is less than or equal to the absolute value of the next term in this series at c, which is a value between x and a. As I said before, if you know the value of c, then there's no need to approximate. However, in most cases, c is difficult to find. This is why we use the error bound. We want the bound on the error to be equal to or larger than the remainder. To do this, we must make the n+1 derivative of f at c as large as possible. In other words, we want to find the worst case scenario. For example, when we're using the sine and cosine functions, we know that the worst case will always be 1, because that is the maximum value of those functions. Now I'm going to show you how to do one of the AP problems that has to do with the Lagrange error bound. This is from the 2011 exam. It's the 6th question. The part D states, let P4x be the 4th degree Taylor polynomial for f about x equals 0. Using information from the graph of y equals the absolute value of the 5th derivative of f of x, shown above, show that the absolute value of P4 at 1/4 minus f at 1/4 is less than 1 over 3,000. Now, this problem doesn't ask you to use Lagrange error bound, but you can tell that you will need to because of that expression, the absolute value of the approximation minus the exact value of the function. As soon as you see this expression, you know that the problem will have to do with the Lagrange error bound, because we need to find the difference between the approximation and the actual value. Now we can just substitute in the values into the formula for the Lagrange error bound. So P4 at 1/4 minus f at 1/4 is less than or equal to the 5th derivative of f at c, which I'll add in later, I'll explain that, times 1/4 to the 5th. It's 1/4 because x is 1/4 in this case, and a is 0 because this is a Maclaurin series, which is centered about 0, all over 5 factorial. The reason it's 5 is because it's n+1, and n in this case is 4. Now, conveniently, the problem gave us a graph of the 5th derivative of f, and we know that c is somewhere between 0 and 1/4 because it has to be between a and x, so we're looking for the maximum value between 0 and 1/4, and that's somewhere just below 40. But to be absolutely sure that we're getting the maximum error bound, we can just put in 40 instead of trying to estimate some number below that, because that wouldn't, we need to be absolutely sure. So I just put in 40 there. And if you do the calculation, which might be a bit difficult since this is a no calculator problem, but you can leave it simplified, you get 1 over 3072, which is definitely less than 1 over 3000. So if you just think about it, the using the Lagrange error bound in the AP problems actually isn't that difficult. I'm going to do one more example, this time from the 2010 FRQ. In part C, we figured out the fifth degree Taylor polynomial for g about x equals 0. I'm not going to show how exactly to do that, because I'm assuming you already know about the Taylor series. And part D says, the Taylor series for g about x equals 0, evaluated at x equals 1, is an alternating series with individual terms that decrease in absolute value to 0. Use the third degree Taylor polynomial for g about x equals 0 to estimate the value of g at 1. Explain why this estimate differs from the actual value of g at 1 by less than 1 over 6 factorial. Now, something important to remember about alternating series is that if the series alternates, the absolute value of the remainder is less than or equal to the value of the next term. Oh, but before I go on, to find the third degree Taylor polynomial for g about x equals 0, you just substitute the 1 into the fifth degree one that you found in part C. So anyway, if the series alternates, the remainder is less than or equal to the value of the next term, and this is because the absolute value of the terms goes to 0. The terms of the partial sums of the series go back and forth around the limit or the value that they converge to. So the error is the difference between the sum, the partial sum, and the limit. But if you add another term, that makes the next partial sum go past the limit. So you can just use the next term as the error bound, because it's greater than the error. Now we can write the expression for the remainder, which is g at 1 minus 37 over 72, which is what you get for the third degree polynomial. And that has to be less than the next term, which you can figure out by using what you got in part C. And that is definitely less than 1 over 6 factorial. So that answers the question. So if you see that it's an alternating series, you don't even have to use the real Lagrange error bound. You just have to know that it's less than the value at the next term.